There's another very important reason to use reductions, and that gets us closer to our goal of being able to classify the difficulty of problems, and that's to establish lower bounds. So let's take a look at that. So what we want to do is come up with a proof that a problem requires a certain number of computational steps. And we had an example of that for sorting. We showed that in the decision tree model, any compare-based sorting algorithm has to use at least n log n compares in the worst case. And we showed that by showing that no matter what the algorithm is, it has to distinguish between all the possible cases of sorting, and that led us to a tree that has n factorial leaves on the bottom, and the height of the tree has got to be at least log of that, which is n log n. And you can go back to the sorting lecture and look at that. Now, that's a complicated argument that certainly took you a little while to understand. And in general, it's extremely difficult to establish lower bounds because it generally requires a complicated argument like that. You have to be arguing about all possible algorithms, and that's very often tough to do. Initially, there was a lot of optimism that we'd be able to have lower bounds as researchers worked more and more, and we'd be able to classify problems. It's actually worked out pretty difficult to get non-trivial lower bounds for all kinds of computational problems where people thought it would be easy. But the good news is that reduction allows us to take the ones that we have and spread the lower bound. If we can reduce sorting to a new problem and without too high a cost of reduction, that gives us an n log n lower bound on that problem. So let's see how that works. We have to make sure the cost of the reduction is not high. That's key. And actually, most of the time, like in the examples that we've looked at, we use linear time reductions. So that is, we only use a constant number of calls to y, and we use just a linear number of steps. So usually we're going through everything in the input, the output to do some kind of conversion. And that's what we've done in all the examples that we've seen so far. Then the idea is, though, if there's a lower bound for x, and you reduce x to y, that establishes a lower bound on y. Right? So why is that? If I could solve y more quickly, then I could use the reduction to solve x more quickly. So if I have a reduction from x to y, and there's a lower bound of n log n and x, I can't have a linear algorithm on y. Because if I did, and I have a linear time reduction, that would give me a linear time algorithm for x. Same way, if I have a lower bound of n squared for x, I can't have an n log n algorithm for y, because if I did, since I reduce x to y, then that would give me a linear time algorithm for y. So the reduction allows us to propagate the lower bound. If I could solve y, then I could easily solve x. But I know I can't easily solve x, so therefore I can't easily solve y. It's a very powerful technique, and really where most of our lower bounds come from. So just for an example, let's look at lower bound for the convex hull algorithm. And it's again, convex hull and sorting don't seem so related, but it's actually the case that in any algorithm for convex hull is going to take n log n. And so we start with a more general statement about sorting. Use the so-called quadratic decision tree model. And this is just a detail about the model of computation that makes the idea of comparing a sorting algorithm to a convex hull algorithm, it makes them both use the same operations. So quadratic decision tree, you get not just to use comparisons, but you can use tests like the product of the difference of two numbers, are they less than 0 or not? And those are the basic kinds of operations that you're going to use in the geometric algorithms. And so the proposition is that under this model, sorting linear time reduces to convex hull. So that says, if I can compute the convex hull, then I can sort. Since I can't sort faster than n log n, I can't do convex hull faster than n log n. And the proof of that is not terribly difficult, but the implication is really important. So convex hull algorithms, it was just based on that idea, am I making a right turn? That's called a CCW test in computational geometry. I have 3 points, and going from first to second and third, is that a counterclockwise turn? And then you can implement that test with these kind of quadratic things. It's just testing the slopes of two lines and comparing them. So it's kind of like a comparison. The implication of the fact of sorting reduces the convex hull means that you can't solve convex hull fast. And so how do we do the reduction between sorting and convex hull? And again, I have a sorting instance. I have some numbers to sort. And what I want to do is create a convex hull instance that gives me the sort. Well, all we do is we take the numbers that were supposed to be sorted and we convert them into points on a parabola. So we just take x1 and x1 squared and x2 and x2 squared and like that. Those are points on a parabola. Now there's no points, and we give that to the convex hull algorithm. Now all of those points are on the convex hull. And the convex hull algorithm is supposed to return them in clockwise order. And you can see with just finding the smallest, that gives us the points in sorted order. So the convex hull algorithm does its job however it does it. We can take the solution to the convex hull algorithm and get a solution to the sorting algorithm. Sorting reduces the convex hull. Therefore, convex hull can't be easy because that would make sorting easy. This kind of thinking is really profound, and it has really done a lot to enhance our understanding of the difficulty of different algorithmic problems. So that's the proof that I just explained. This parabola thing is definitely going to be convex, and all the things are on the hull. So we just get the point that's got the most negative x coordinate, and you got the integers in order. So establishing lower bounds through reduction is really important. We have a big convex hull problem to solve, and we're wondering, do we have a linear time algorithm for this? It's a quite natural thing to wonder. And so how are you going to convince yourself that there's no linear time convex hull algorithm? One thing you can do, and believe me, a lot of people did this, is just try to find a linear time algorithm. Keep working at it. Keep working at it. You're going to use algorithms that are based on this simple kind of comparison between points. It doesn't seem like it should take n log n. It seems like we should be able to find a linear time algorithm. Well, that's the hard way. The easy way is to know that reduction from sorting, and that means there's no point into trying to put in our effort to try to improve on the grand scan. Grand scan gets it done in n log n. We can't do better than n log n, so we might as well call it a day and move on to some other problem. That's an example of reduction for proving lower bounds to help us guide our algorithm design efforts.